Welcome back, mathematicians. We are now on to section 4.4, concavity and curve sketching. We did a little curve sketching last time, but now we have, after this section, all the tools to sketch a curve. All right, so first thing we're going to talk about is concavity. So we have two different options, just like we had two different options for increasing and decreasing. So we're going to have concave up and concave down. And there's a trick to knowing what these look like. So I'm just going to draw a cute little graph for you guys. All right, so this section of the graph kind of looks like the side of a cup. That is concave up. Looks like a cup. Where this one is concave down, like a frown. Right? So we're concave up right here and concave down in the green. That's how we can kind of look at a graph and figure out if we're concave up and concave down. And we'll talk about this little middle part too in a second. So let's define them so we kind of have a better understanding. So we say that the graph of y equals f of x is concave up if on an open interval f prime is increasing. Well, we learned last chapter that if f prime is increasing, its derivative is positive. So that means that f double prime is greater than 0. Similar for concave down, if on an open interval f prime is decreasing. We know that is when f double prime is less than 0. With these definitions, we have the second derivative test for concavity. All right, so if f double prime is greater than 0, the graph of f is concave up. And if f double prime is less than 0, the graph of f is concave down. Simple as that. All right. So let's do an example. So if we choose y equal to x cubed, we know that its derivative is by power rule 3x squared, and y prime, double prime, excuse me, is going to be 6x. Perfect. Well, y double prime is only going to be negative if x is negative. Wait. And y double prime will only be positive if x is positive. We can also write that as an interval, right? So from negative infinity to 0 and 0 to infinity. So we can then write that y equal to x cubed is concave up on 0 to infinity and concave down on negative infinity to 0. Alrighty? Well, what about x equals 0? What's happening there? So just like we had critical points and extrema, we have for increasing and decreasing in our first derivative, we're going to have possible inflection points and points of inflection for concavity in the second derivative. All right, so we can define those. So a possible inflection point, I also call them pips, is wherever f double prime of x equals 0 or is undefined. All right, and then, so that was for a possible inflection point. An inflection point is a possible inflection point, a pip, where the concavity changes. Like we saw in the first derivative test for extrema, a max and a min, the direction of the graph has to change from increasing to decreasing or decreasing to increasing. An inflection point here has to change from concave up to concave down or concave down to concave up. All right? So let's do another example. And we're going to make a similar chart that we did before, but instead of plugging into f prime, we're going to plug into f double prime, or y in this case, because we're given y equals x to the fourth, and we are asked to find, if I can find the question. Yeah, all inflection points, if they exist. Okay, cool. Yeah, so if y equals x to the fourth, we need to find y prime, so that's 4x cubed, and y double prime is 12x squared. So that, we want to set that equal to 0, right? To find our possible inflection point. So I set 0 equal to 12x squared. That gives me x equals to 0. I'm going to write my little chart over here. I'm going to plug in -1 and 1. Okay? So if I plug in -1 into, I'm not going to write f double prime because I don't have that. y double prime. Well, that's going to give me 12. And if I plug in 1, I'm also going to get 12. All right, so that's a positive number, so they're both going to be concave up. I like to draw a little cup like that. So then we can conclude, since the concavity is not changing at all, that x equals 0 is not an inflection point. Alrighty. Let's do another one. So we're given y equals x to the 1/3. So y prime will equal x. Oops. So the 1/3 will pop down, and we have x to the negative 2/3. And then y double prime will get negative 2/3 times 1/3. X to the 2/3 minus 1, which is negative 5/3. Simplify that to negative 2, 9 divided by x to the 5/3. All right, 3 times 3, that's how I got the 9 in the denominator. And then x to the negative 5/3, technically in the numerator. So if I bring it down to the denominator, that's when I get x to the positive 5/3. All right, so clearly y double prime is undefined at x equals 0, right? Undefined means when the denominator equals 0, and that only exists when x equals 0 in this case. So that's going to be our critical point. So I have 0, draw my line under it. I like to choose really easy numbers like negative 1 and 1, y double prime. So I plug in negative 1, and I get, let's see, negative 2 divided by 9 times, what's that? That's also going to be negative 1. So that's a negative divided by a negative, so that's a positive. And then if I just plug in 1 to the 5/3 will give me 1. So I'll get negative 2 over 9, which is a negative number. Okay? So here, I'll put those numbers in. Again, I just like to do the signs. It's a lot faster. So then we see that we are concave up, and then we are concave down. So that is a change in inflection. So we can confirm that x equals 0 is an inflection point. Or there is an inflection point at x equals 0. Because a point has x and y, so my pen is being so weird. So 0, 0 is an inflection point. Woo! Okay. So notice if I draw a generic concave down graph, just like a big frown, I'm gonna have an extrema right there. Well, I can look at the graph and I can tell that that's a max. And a generic concave up, a cup, if there's a horizontal tangent, it's going to be at a minimum. This is why pictures really, really help. So this yields the second derivative test for local extrema. So we had the second derivatives for concavity and inflection points, and now we have the second derivative for local extrema. So okay, we're just gonna call extrema EXD for simplicity stakes. All right, cool. So we're gonna suppose F double prime is continuous on some open interval. If it's not continuous, then this doesn't work. So first conclusion we can get is that if f prime of c is 0 and the second derivative at c is less than 0, so concave down, then f has a max, not just a max, a local max. At x equals c. If the first derivative is 0 at a point and the second derivative is positive, f is concave up, thus f has, as a local min at x equals c. Well, what if the second derivative equals 0? So if both f prime of c and f prime double prime of c equals 0, then the test fails. So I don't know. It could be a max, it could be a min, or it could be neither. I don't know. So then I would probably revert back to the first derivative test, which won't be too bad because I already have the first derivative. That's how I got the second derivative. So if you like the first derivative test more, do that one. I usually do just because it doesn't really have a chance of failing. And sometimes it's kind of hard to find the second derivative test, but when I need to find concavity, I already need to have to find the second derivative. Okay, so now we're going to walk through an example that has a few parts. Okay, cool. So we're given that f of x equals x to the fourth minus 4x cubed plus 10. All right, and we're then asked to find where the extrema occur. Okay, cool. Yeah. Sorry, there's two parts and I thought about combining them, but I don't feel like it right now. So we're going to find the first derivative and set it equal to 0. So 4x cubed minus 12x. right? We'll set that equal to 0. Let's factor out a 4 and an x, so that I'm left with x squared minus 3. Oh, wait. That's squared. Okay. There we go. So I pulled out a 4 and an x squared. Okay, cool. So this tells me that either 4x squared is equal to 0 or x minus 3 is equal to 0. So that yields x equals 0 and x equals 3 as critical points. Not extrema, just critical points. So now we're going to make our chart. I'm going to choose some x values. Let's choose -1, 1, and 4. I'm going to plug those into f prime and see what number I get out. So if I plug in -1 into here, any number I plug in here, since x squared only gives me positive numbers, so this is always going to be positive, so only x minus 3 is going to give me a differing opinion, okay? So -1 into x minus 3, it's going to give me -4, so that's a negative. I plug in 1 minus 3 is -2, that's also going to give me a negative number. And then 4, I'll get 4 minus 3, which is a positive number, times a positive number. It's going to stay positive. All right, so we're increasing and then increasing. Oh, wait, backwards, sorry. I looked at the wrong thing in my notes. Decreasing, decreasing, and increasing, right? So we're going down, down, and then back up. So right there we can see that 1, not any type of extrema, but 3 is going to be a local min. Perfect. So we can say that f of x has a local min at x equals 3. Okay? So now part B asks us to find the intervals where f is increasing and the intervals where f is decreasing. Great, we've already done that with that chart that we already drew. So remember, the only time we can change from increasing to decreasing, if our derivative is negative and positive, the intermediate value theorem says that it has to intersect 0, right? Polynomials are continuous. So if at all the way from every number less than x equals 0 is negative, I tested one number, so they all are going to be negative, all right? So that means that, and same for any number greater than 3, it's increasing at that one test point, so it's going to be increasing in all the points greater than 3. So we can say that we are increasing on 3 to infinity, and we're decreasing negative infinity to 0 and 0 to 3. Okay? And now we're asked to find where f is concave up and concave down. Alrighty, cool. So we have our first derivative right here. So let's rewrite him. So f prime of x equals, and I'm not going to use the simplified one because power rule is a lot easier than product rule. Okay, cool. So then I'm going to take the derivative of this to get to my second derivative. So 3 times 4 would give me 12x squared minus 24x. And then I can pull out a 12x. So then I'm left with x minus 2 as a factor. Beautiful. And so we're going to set this equal to 0. Meaning that 12x equals 0 or x minus 2 equals 0. Oops, not 2 equals 0. So we get x equals 0 and x equals 2 as possible inflection points. All right, so let's draw our little chart. So x, we're going to plug in -1, 1, and 3. We're going to plug these into f double prime. So -1 will give me -12 times a -3. So negative times a negative is a positive. If I plug in 1, I'll get 12 times 1 minus 2, which is -1. So I'll get -12. So minus. And then 3, I'll get 36 times 1, which is a positive number. So I am concave up, concave down, and then concave up again. So I would then conclude that x equals 0 Sorry, the book had something different. We are going to ask for concavity, not inflection points. So we are, why can I not spell today? I can never really spell. So we are going to be concave up from -infinity to 0 and 2 to infinity. And then we're going to be concave down from 0 to 2. Just in that little spot. All right, so the last two parts, I think they put out of order. Yeah, so we are going to D and E. We're going to plot some specific points. So local max. Or we don't have one of those, but if there was one. Local min. Inflection points. Intercepts. So like y and x intercepts. And then sketch the graph. Because I know where it's concave up and down. I know where it's increasing and decreasing. So before we do this, I want to kind of give you guys a little chart. So for decreasing and concave up, it's going to look like that. If we are increasing and concave up, our graph will look like that. If we are decreasing and concave down, I can do that a little better. It'll look like that. And if we're increasing and concave down, we are going to look like that. Okay? So think of just like the other sides of a cup and a frown. Okay, so now we have that little blurb, and that'll help when drawing this masterpiece. So let's remember that our function is f of x equal to x to the fourth plus 4x cubed plus 10. So when x is 0, f of x is at 10. So let's make each one of these blocks 10, like 2. So yeah, right there. And then, so make that 2, 2. And we had an inflection point at 0 and 2. So this is an inflection point. The function at 2 is -6. So we'll be right here is another inflection point. And then 3 was our local minimum. Right, so if we scroll all the way back up here, we saw there was a local min at x equals 3. And that function value is at -17. So where is that going to be? 1, 2, 3. So like right here. Okay. I think those were our 3 points. All right, so I like to start to the left. So to the left of my inflection point at 0, we were concave up. And then I'll scroll back up here, see if we're increasing or decreasing. We are decreasing. So we're concave up and decreasing. So we're going to look kind of something like this guy. And then from 0 to 2, we were concave down and still decreasing. So it's going to kind of look like, beautiful. And then after 2, we're concave up for the rest of the time. And we're going to be decreasing until 3 and then increasing after 3. So now we're going to kind of make like a cup and then go up and up and up and up and up. Oops. Let me redraw that. All right, so I like that. Mostly a better curve. All right. So we can kind of look now after graphing all those things that this is not only a local min, but it's actually an absolute min. So let me label these points. This one is 3, -17. inflection point was at positive 2, negative 6, and 0, 10 was our other point. Okay, cool. So there is our graph. So now we kind of have a procedure for graph sketching. That kind of gave us a little outline, but there's a little bit more we can do. All right, so the first one is to identify the domain of F and any symmetries, So if it's an odd function, is it an even function, or is it not? You guys know how to do that from chapter 1. All right, so step 2 is we're going to find the derivatives, specifically the first and the second. Doing them first instead of when you need them just has them in like a certain spot, and you can kind of go back in your problem to find them, not like looking all through your work. It's good to keep your work organized. So then step 3 is to find the critical points, if any, and identify the function's behavior. So increasing, decreasing, max and min. All right, so then number 4 is, technically number 4 is when it's increasing and decreasing. I kind of include that in step 3 when I do it, but I kind of want to give you how the book spells it out because I like it's a little bit more detailed. So 5 is going to be to find the points of inflection and determine the concavity. All right, and then 6, we kind of did this in the last chapter, is identify any asymptotes, because that'll also help you find any absolute extrema. And then kind of once we have all of that, we're we're going to plot our key points. So intercepts, and points found in steps 3 through 5. And then put it all together with asymptotes, concavity, and behavior. So we're going to sketch the graph using all other information. So concavity, increasing and decreasing, asymptotes, and everything like that. All right, so we're going to do one more example, and then we're going to be done with this section. And then we'll move on to next, because this one's coming out Tuesday. And then tomorrow's lectures are really fun. So we're going to do this example, and we're just simply asked to sketch the graph for f of x equal to x squared plus 1 squared over 1 plus x squared. All right, so step 1, domain and symmetries. So this is a polynomial over a polynomial. I don't see any place where I can't plug in a number into the denominator. 1 plus x squared is always positive. It's not going to give me 0 ever. So the domain is negative infinity to infinity. And again, there are no symmetries. Okay, cool. 2. Now we're going to find the first and second derivative. So f prime of x, it says quotient rule. So we're going to be low, d high, so it's 2 x squared plus 1 times 2x, write the derivative of the outside with the inside still the same, times the derivative of the inside, minus, so that was low d high minus high d low, which is just 2x, all over low squared. And I highly suggest simplifying this. So each term has a x plus 2 and an x squared plus 1. So I'm going to pull out a 2x and an x squared plus 1. And that's going to leave us with 1 plus x times 2 minus x squared plus 1. All over 1 plus x squared squared. I forgot that. There we go. So 2x. Sorry, my pen is like going in and out. There we go. X squared plus 1. So what's this inside going to get me? Negative x squared plus 2x plus 1 minus 1. So there we go. Make sure that's what the textbook got. Oh, there it is. That's a squared. So then this is a squared. One second. Oh, I'm dumb. Okay. One second. We're gonna get rid of this. Okay. So I'm gonna simplify each term. So this is gonna be 4x, x squared plus 1. I wrote this problem wrong. It's x plus 1 squared over 1 plus x squared. Goodness gracious, I can see. Okay. So low, d high. Minus high, d low. Yes, okay. Over low squared. I'm so sorry about that. I was taking an exam, like a final exam, and I could not get the answer to this problem. I was like, it doesn't make sense. I just don't understand. Like, how am I supposed to conclude this? I was trying to prove it, and it's because I wrote it wrong. So make sure that you copy down your homework right and do the problem, the actual problem given. Okay, cool. So now there is a 2x plus 1. There we go. I can pull out from each term. And that left me with 1 plus x squared minus x plus 1 times x. And all over 1 plus x squared, that quantity squared, 2x plus 1, 1 plus x squared minus x squared minus 1. So then those cancel out, those cancel out. Okay. The book just did that all in one step and I was confused. Okay, so this gives us a grand total of 2x plus 1 over 1 plus x squared squared. This is a lot easier to handle than this first jumbo mumbo that I got. All right, so that is f prime of x. We are going to highlight it. Oh, hi, Winston. And then now we can find f double prime of x. We're going to have to do chain rule again. Please don't lay it on my textbook. No, you can't lay it there. Okay. That's fine. Damn it. Okay. So do low, d high, which is just going to give us 2 minus high, d low, so it's going to give us 2 x squared plus 1 times 2x. Oh, that's what I was reading earlier. Boop, okay. And then the bottom squared again, so that's going to be 1 plus x squared, everything to the 4th. So I am Confucius. apparently my first derivative is wrong. Okay. I'm annoyed. How do they get that? Okay. So I'm going to give you what they did in the textbook because I'm frustrated and that is fine. And mistakes happen. So this simplifies to 2 times 1 minus x squared over 1 plus x squared squared. So we're going to move this up. I have been stuck in my apartment for too long. Okay, cool. So then f double prime, we get to do quotient rule again. And that's going to be low, d high, so 2 times a negative 2x minus 1 minus x squared, which is high, and then d low, which is going to be 1 plus x squared times, that was the derivative of the outside with the inside still the same, times 2x. This is all over 1 plus x squared squared. And then when we simplify it, we'll get 4 x squared minus 3 over 1 plus x squared cubed. Okay, cool. So we have both derivatives and we have them simplified too. So we're going to highlight them. Okay, so step 3 is to find critical points of f, if any, and identify the behavior of those points. Okay, so now we are going to set the first derivative equal to 0 and also find where it is undefined if possible. So we're going to set 1 minus x squared over equal to 0. So that really means we're only going to look at where the denominator equals 0. So we're only going to look at where 1 minus x squared is equal to 0. So divide each side by 2, and we'll get 1 minus x squared equals 0, x squared equal to 1, and that gives us x equal to plus or minus 1. And then we can look at where the denominator equals 0 because that's where we're undefined. But we can see that that's not ever going to happen. So if we have like 2 times 1 minus, no, 1 plus. So we at the wrong place again. One plus x squared equals 0. So that's if I square root both sides, square root of 0 is 0. And then x squared would have to equal -1. And that's not happening. So we are not playing around with imaginary numbers. So our only critical points are +1 and -1. So since we already have our second derivative, let's just plug in to this, do the second derivative test. So I'm going to have -1 and 1. And I'm actually going to plug those into the second derivative to see if they give me a positive or negative, and that'll tell me if there's a max and a min. So if I plug in -1 into the second derivative, I'm going to get -4. Yeah, let's move this over. I'll get what? -4, 1 minus 3 over 2 cubed, which is -4 times -2, which is 8 over 8. So that's 1. That's positive. And then if I plug in 1, I'll draw a little line between them. I'll get 4, 1 minus 3 over 2 cubed again, which is just the negative version. That gives us a -1. So concave up is a cup, concave down is a frown. So that means there is a minimum at -1 and a maximum at x equals 1. Or local ones, okay? So let's make note of that. A local min at -1. F of -1, we'll figure that out later. And a local max at 1, F of 1. All right, cool. So now we need to find where we're increasing and decreasing. This is sometimes where I like to use the first derivative test because then I already have where I'm increasing and decreasing. So we're going to have our critical values. So -1, 1. We're going to have our test points. And then we're going to plug those into the first derivative. And see the sign and behavior from there. So if I plug in, love to plug in 0, and let's do -2 and 2. So f prime is 2, let's come down here and write it again. It is 2, 1 minus x squared over 1 plus x squared, that quantity squared, right? Okay. Don't want to write it wrong and go through that. So if we plug in -2, we'll get 2 times 1 minus 4. So it's like -3 over, let's see, 1 plus 4. So it's 5. 5 squared is 25. So that's going to give us a negative number. If I plug in 0, I'll get 2 times 1 over 1, so that's a positive. And then for 2, I should get the same thing, right? 2 times -3 over 25. And that's a negative. Beautiful. So we are decreasing and then increasing and then decreasing. And then I like to write out my intervals. From -1 to 1, we're increasing, and then we're decreasing everywhere else. Alrighty, so next we need to find our inflection points. So we're going to set the second derivative equal to 0 or undefined. So what is the numerator? Where's my second derivative? 4x, x squared minus 3? Yeah. So f double prime of x equals 4x, x squared minus 3 over 1 plus x squared, that quantity cubed. So just like what we saw earlier, the denominator can't equal 0. It only gives me numbers greater than 0. So we're only going to focus on the numerator. So 4x, x squared minus 3. Well, that means that either 4x equals 0 or x squared minus 3 equals 0. So we get x equals 0 and x equals plus or minus the square root of 3. Now we need to make sure they're inflection points, so we need to check the concavity. So let's see. Negative square root of 3, 0, and the square root of 3. I think the square root of 3 is like something like 1.7, because, no, it should be more than 2. Calculator. No, yeah, because the square root of 4 is 2. So this should be, yeah, 1.7. Great. So our test points, boom. I'm going to choose -1, 1, 2, and -2. I'm going to go back to the second derivative on those. So if we look at the the denominator, it's always going to be positive. So I kind of don't even need to plug into there because that's always going to give me a positive outcome. And a positive, if I divide by a positive number, whatever the numerator is, it's going to stay that sign. So I kind of only care about the numerator. So plugging -2 in, I'll get -8 and then 4 minus 3, which is 1. So that is a negative and concave down. If I plug in -1, I get a -4. 1 minus 3 is another -2, so that's +8. Concave up. What's happening at 1? 4 times a -2, so minus concave down. If I plug in 2, I'll get 8 times 4 minus 3 is 1, so I'll get a positive number. And we're concave up. Okay, perfect. So now when you look for any asymptotes. So, well, let's state our inflection points. They're at negative square root of 3. Plug that into the function. And the square root of 3. Oh, wait, positive. There we go. Cool. And then we are concave up from square root of 3 to 0 and, negative square root of 3 to 0 and square root of 3 to infinity. Concave down, negative infinity to -3, and 0 to square root of 3. That negative needs to be a little bit more prominent. There we go. Okay. So now we need to find any asymptotes if they exist. So that includes vertical and horizontal. So let's first look at horizontal. Remember, we find horizontal as x goes to infinity. Horizontal. Let's do those first. So we'll do the limit as x goes to infinity of x plus 1 squared over 1 plus x squared. And if we expand the numerator, so we'll get x squared plus 2x plus 1. Kind of wish I did that earlier when I was taking the derivative. Oopsies. Don't drop your limit. Those things aren't equal without the limit sign. So if you do the dividing by the greatest power in the denominator, we get that the limit is equal to 1. So we have one horizontal asymptote at y equals 1. So if we do it as x goes to negative infinity, x plus 1 squared, 1 plus x squared. Once we do the same thing, since the square is the highest power, we're still going to get 1. Okay, cool. So we just have one horizontal asymptote. Horizontal. I really wish I need to learn how to spell. There we go. At y equals 1. Okay. So vertical asymptotes. That's when the denominator equals 0, but 1 plus x squared cannot ever equal 0. So there's no vertical asymptotes. We'll call them VA. Alrighty. And so now we're going to sketch our graph. So, a line. Okay. I like to do my max and mins first. So I'm going to scroll up and find my local min and my local max are at -1 and 1. So -1's here. Let's actually make this a little bigger because that'll help me. Let's make a -1 here and 1 here. 1 and 1. -1. Okay. So, right, f of x equals x plus 1 squared over 1 plus x squared. So f of 1 will equal 2 squared over 2. So that's 4 over 2, which is just 2. So 1, 2. So that was our max. F of -1, that's going to give me 0 over 2, which is just 0. That's nice. And then, what else? Oh, yeah. My inflection points were at 0. And plus or minus square root of 3. So if we plug in 0, I get 1 over 1, which is just 1. That's nice. That's an inflection point. Oopsies. Let's make our inflection points a different color. I'm gonna make them, I think of them in blue. Make them blue. And then f the square root of 3 is somewhere under 1. I don't have a calculator, but I think it's right around here. And then the negative square root of 3 is right around here. Ooh, little spot. Okay. Oh my gosh. Okay. There are my inflection points. And then our horizontal asymptote will be in red. Remember that we can cross a horizontal asymptote. It's just our end behavior. It doesn't mean we can't ever exist there. Vertical asymptotes, we can't really ever cross those because that means we're divided by 0, and that is not cool. So we're first going to be concave down and decreasing. So, and we are going to start below the horizontal asymptote. So we're going to look kind of like that. Right? We know that we're below because we have these 2 points that are below the horizontal asymptote. And now we're going to be concave up. And I'm going to intersect my minimum. So I'm going to kind of make it look like a fun little cup. Like that. And now we're concave down and increasing. And now we're concave down and decreasing. And now we're concave up again and decreasing. And just like that. I might have drawn a little too big of a graph, but that did take a while, I will agree, but with more practice, it won't take as long, I pinky promise. And when you have a calculator and can punch in numbers like I didn't. All right, so this was a really long lecture. It's your only lecture of the day, so I'll see you guys tomorrow. Have fun.